Okay, next we have Hualin Wu from Terapines.
Hello. Okay, can you hear me? Okay. Let's get started. So today I'm going to share the. So this is a real demo, not a presentation. So I'm going to share you how to use our toolchain, the ZIG solver, to build a SOC to accelerate an AI application. So this video will show you how to build the virtual SOC, run the application on the virtual SOC, and analyze the bottleneck of the application, and tune the microarchitecture of the hardware, or add customize the instruction to the SOC. So and finally, you can see how much performance is improved by doing so. Here we go. This is our IDE in a browser. So you can see we have a listed of virtual IP there, and we have also lots of components in the left bottom side. So you can build a virtual SOC by drag and drop those virtual components into a GUI interface. So we use Andis D45 as example to show our virtual board builder. So you can see, so this is a virtual SOC for Andis D45. It consists of the Andis D45 CPU, iCache, Dcache, and the memory bus. And by clicking on the components, you can see on the left side, there are lots of the attributes you can edit, such as the name of the components, MSHRS, and the cache size, etc. So all the virtual IP we provide within the Explorer are configurable. So you can follow System C or our API to define your customized virtual IP. So if there are missing from our library, so you can also plug in RTL model into our ZIG Explorer as well. So some IPs, such as CPU, are modeled in greater detail. So you can just click into the IP and click open. You can go into the CPU pipeline detail of the microarchitecture. You can modify the CPU pipeline by adding components, edit the attributes, or even add customized instruction to the ALU. So, okay, let's import AI application, the speech recognition in our Z Studio to say how can we accelerate this AI application with our virtual platform. So firstly, we can import this project with the same make importer. Okay, you can configure all the same make options and set up the build flags and environment variables for the project. So now the AI application is being imported. So we can import the weights for the speech recognition. So firstly, we need to locate the trained parameter for the keywords recognition. So we can double-click the AI model to see the network architecture of the AI model. And so you can see how each layer presents on the canvas. And so after that, you can right-click and generate a C code for the model. So you can generate all the weights and the parameter for the trained model, and which will be used in our project later. Okay, here's the generated C code. Okay, now let's add the weights to our project. So let's select the C array file, and this C file contains all the weights and the parameters for this speech recognition application. Okay, here is the weight file. So as we previously have already imported the model data, so we'll use the original model data for example. So this is the one we have just pre-generated. Okay, now let's build the application, and we can run the AI application on our virtual platform. So let's configure the platform which the application will be run on. We can choose simulator or real boards. Now here we choose the simulator, and we have a nodes of near cycle accurate model built in with our IDE. Let's click run. Then, okay. Now this application is running on our virtual platform. Okay, we will go through the profiling of this application to say what's the actual performance this application runs on Andes D45. Okay, we are going to generate the coverage information for this application as well. So we need to modify some compiler option in order to align the source code with the assembly code. So we will change the optimization level for this compilation to 0 to align the line number to the source code. So after running, let's wait for a second. So we are going to rebuild the kernel in 0 to get the coverage information. Okay, let's show the program summary, which will highlight the function list of from top to down to say. So this is ordered by the self cycle of the execution of the program. You can see the first function takes most of the time to run. So we can click the C button to go into the coverage information of the actual program. And you can see the most executed code is in the for loop. So we can design a customized instruction to accelerate the for loop with our Z Explorer. So here we have added 3 instructions. They are vector product, so V dot, and V sub E32, which is and VLB sign extend. Those 3 instructions will be used to accelerate the speech recognition. So now we will generate the compiler and the simulator for this instruction. Okay. Here is the view of how you can define a new customized instruction. You can specify the function unit which the instruction belongs to, and the latency of the instruction, and the encoding bits, and the architecture of the instruction. And you can also specify all the encoding fields of the instruction within this table. And also you need to describe the simulation behavior of the instruction at the bottom. And by right-click the ZME extension, we can generate shared library, which will be used by our compiler and the simulator. So this shared library supports those customized instructions. OK, let's create another virtual SoC of NDSD45, because we are going to modify the virtual board to have those customized instructions. So we name it NDSD45 accelerated. So we select the D45 in the canvas, and we can add the ZME extension from the extension drop-down menu. So we choose the ZME extension we previously created. So that's done. So this board is already associated with our customized instruction. So now we are going to modify the application to have the header file included and the inline assembly included. So the original code is replaced with the inline assembly. Now we are going to add the extension to our compiler option and rerun the profiling. So we are going to rerun the profiling. So we are going to choose the virtual board we just created. So it's NDSD45 accelerated. So let's do the profiling. And then you can see the program summary and the function summary already presented. And here you can compare the profiling from the profiling results. Here is the comparison of the same projects on two different virtual boards. You can see there's roughly 50% performance improvements against the original application. You can try this demo online. Yeah, thank you.
Thank you so much. Thank you.